Good afternoon to you all. Today we will start the first chapter on probability theory. And before we dive into the theoretical rigor of probability theory, I think it is a good idea to start with some very simple examples concerning discrete probability theory, where we will try to solve some examples using objective approach of probability theory, and the focus would be not to rely on formulas, but rather on the ability to solve the problem using what is given and what is required. And to illustrate this, I would take some examples, very simple examples on probability theory. For example, the first example would be if you have a class of some students. Let us say you have a class of 65 students, typically the strength of any master's class in IIT Madras, and you ask yourself a question: what is the probability that any two of them will share a birthday? Any two students in the class sharing a birthday. Okay. Now, this is a very interesting problem. In fact, if you look it up in the web, or if you look it up in basic textbooks on probability theory, there is an analytical result which says that you require about 23 students in a class such that the probability of any two students having a birthday which is same exceeds 50%. So, that is a result you can derive at the end of this in this problem, but I am going to basically pose a simpler question, that you have a class of n students, n being 65 here. What is the probability that two students will share a birthday? Okay. So, this problem can be done objectively, in the sense that you can say that, let us say you have P0 as the probability of nobody sharing a birthday, which means all the 65 students have different birthdays, plus you say two of them share a birthday, and this way you take 3 of them, 4 of them, so on, all the way to, let us say, all 65 of them sharing their birthdays. Okay. Now, I know that the sum of all these probabilities has to be 1, because all of them have an exact birthday, and I have taken all the possible cases on the left hand side, this last case being all 65 students having birthday on the same day. So, this is the left hand side is exhaustive, collectively exhaustive. So, sum of all this has to be 1. What is asked is basically that what is the probability that at least 2 students, I should slightly correct my question. And then if the question is at least 2 students sharing a birthday, that is basically the sum of all these P2, P3 up to P65. Okay. So, this is basically my answer P of A, and I have P0 which is nobody sharing a birthday. So, P0 plus PA should be 1. Okay. So, which means my answer is now PA equals to 1 minus P0, which is nothing but 1 minus the probability that nobody shares a birthday. Okay. Now, the fact that nobody shares a birthday is a problem of simple permutation. Since you have 65 students and you want to write down the probability that nobody shares the birthday, you can say that the first student has 365 days in the year to take as his birthday, divide by 365. Okay. Now, the next student who comes has 364 days available, because the first student has already taken one birthday in the calendar year. So, he is left with one less day. Okay. The third student who comes sees that the first two students have already taken 2 days in the year. So, his number of days accessible is restricted to 363 out of a total of 365. Okay. And this way the last student has only 301 days available, and that is the probability of his birthday being one of them. So, now you can basically write this as 1 minus 365 into 364 into 363 all the way to 301 divided by 365 to the power 65. Okay. And this can be written as 1 minus 365 factorial upon 300 factorial into 365 by to the power 65. Okay. And if you solve this, the answer that you get, you compute it in a calculator, or you can use a simple Stirling's approximation that I can write down this 365 to the power. So, because this is a large number, for large number a factorial can be written as, if n is large, n factorial is n by e to the power n. Okay. So, I can write this as 1 minus 365 by e to the power 365 upon, now of course, I have to write down a nearly equal sign here because I have used a Stirling approximation, over 300 by e to the power 300 into 365 to the power 65. Now, if you solve this, your answer would be, I have not calculated this, but you can use a calculator to proceed from here. Okay. So, I leave that as an exercise. This answer should be greater than 70%. Okay. So, the exact answer can be computed by using a calculator, but it would be definitely greater than 70%. Okay. Now, so this is the this is an example of doing this problem objectively without using any formulas. So, there is one more problem that I would like to immediately discuss, which is basically a problem of letters. So, I will take the second example, and you basically, let us say that you have 4 letters, and the letters I spell them out as A, C, T and G. Okay. And suppose these are the 4 letters that are they basically represent monomers in a peptide chain. So, you have a chain of monomers which is basically composed of only these 4 letters, okay. And you say that my peptide chain is 9 monomers long, okay. And you ask yourself a question that, so I have 9 monomers, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, this is your typical peptide chain, and the empty slots have to be filled with these 4 letters, okay, these 4 letters. Now, the question here is, so what is the probability of finding a sequence A, 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 T, C, G, A, G, T, okay. So, what is the probability of this sequence? Probability of finding this sequence. Now, you can construct a very large number of sequences. Of these large number of sequences, one of the sequences in front of you, A, T, C, G, A, G, T. What is the probability of finding this sequence out of those very large number of sequences? So, this is already a permutation problem, because here the exact sequence of the monomers is important, because if I would change the relative positions of T and C, then the peptide chain would be different. So, sequence is important here. So, this is a permutation problem. And then to answer what is the probability of finding this sequence, I must first find out the total size of the sample space, which is total number of sequences that are possible. Okay. Now, since there are 9 monomer units, each of them can be taken by these 4 monomers A, C, T and G, which means the total number of realizations that I can construct is 4 to the power 9. Okay. Since each monomer, total 9, we have total 9 of them, is taken by one of the 4, that is A, C, T and G. Okay. So, if you have 9 vacancies and each vacancy can be taken by one of these 4, the answer that how many the answer to the question that how many total what is the total number of peptide chains you can construct, that is 4 to the power 9. And so, the probability of any one sequence is of any one sequence, in this case the sequence mentioned here, is exactly 1 upon 4 to the power 9 or 4 raised to minus 9. That is the answer to the question. Okay. The second question is, what is the probability that you will find a sequence with four A's, 2 T's, 2 G's, 1 C, okay. So, you can see that 4 A's, 2 T's, 2 G's and 1 C is basically total 9 monomers. So, basically you can take 4 A together, okay, then you can take 2 T's together, then you can take 2 G's together and 1 C. But you can also have 3 A's together, then you can put 1 T, 1 G and put another T, another G, 1 A and C, and this way there are many sequences. So, the question asked here is, what is the probability of finding a sequence with 4 A's, 2 T's, 2 G, 1 C. Basically the sum of all these permutations divided by the total number of permutations. So, this is essentially a combination problem, where you do not say that I want exactly this permutation. What you have done is essentially ask the question that I am interested in the total number of ways in which I can get 4 A, 2 T's, 2 G's and 1 C. Okay. So, this is exactly it's different from the previous problem in the sense that you are essentially saying that I do not care about the sequence, all I want is what is the probability of finding 4 A's, 2 T's, 2 G's and 1 C. Okay. So, this can be done in a very simpler way. You can find out the probability of you can find out the total number of. So, the probability of this particular case is given as the number of possible the combinations you can have, which would be, if you have 9 monomers, and this is a multinomial combinatrix, where you will have where you can say that this is equal to 9 factorial divided by 4 factorial into 2 factorial into 2 factorial to 1 factorial. Okay. So, you can see that 4 plus 2 plus 2 plus 1 is 9. So, this is like this is exactly the probability of this is the number of combinations that you can have, and then if you divide it by the total number of combinations, which is 4 to the power 9, this will essentially give you the probability that we are chasing. One way to interpret this is that 1 upon 4 to the power 9 is the, so this is the desired probability. 1 upon 4 to the power 9 is the probability of one sequence, and this this factor, this combinator factor is basically number of such combinations. So, you have number of combinations multiplied by the probability of each sequence in this combination. That gives us the desired probability. Okay, that's your answer. If you work it out, it would come out to be around 0.14, which is like saying 1.4%. Okay, if you work it out. One problem that is important here, that concerns the role of a die. So, if I take a fair sided die, okay, so this is another problem. So, a die is basically a cube shaped object, and on each side of this cube you have a number written on it. Okay, so you can say that the face value of a die is let us say mu. Okay, so the face value is mu, and this mu belongs to one of these digits. Okay, and the question is, how many times I must toss this die such that the probability becomes 2/3, that at least 2 will appear, at least 1 2 will appear, which means the question is, how many times should I toss the die such that the probability of getting at least 1 2 will become 2/3. Okay, suppose if I toss it once, I know the probability of getting 1 2 3 all these digits is 1/6. Okay, so I know that, I know a priori that P of mu is 1/6, where this mu belongs to the set of these 6 numbers. Okay, now you may toss it the first time and you will get 2. So, you got 2 straight away, but it is possible that if you toss it 3 times you may not get a 2, but you get a 2 the fourth time. So, basically how many times should I toss this die such that the theoretical probability of getting at least 1 2 will be 2/3. Certainly you do not have to toss it 100 times, because I know that all these phases are unbiased. So, there is a 1/6 chance of getting a 2 on any trial. So, you do not require a very large number of tosses, but just to compute the minimum number of tosses required statistically to say that the probability of getting 2 will become 2/3. Okay. So, this question can be done in a certain way, that if you know that the probability of getting a 2 is 1/6, you can say that the probability of not getting a 2 is 5/6. Okay. Now, this is saying that if I toss it k times, suppose I toss the die k times, okay, the probability of not getting a 2 would just be 5/6 to the power k. okay, because each toss is independent of the previous toss. The probabilities are multiplicative. Dependent. So the probabilities just keep on multiplying. Now, the question that was asked was, what is the probability that the occurrence of 2 becomes 2/3, which means if I know that the probability of I can say that after k tosses, the probability of getting at least 1 2 would be just 1 minus 5 by 6 to the power k, right, because there are only two options, either you get a 2 or you do not get a 2. 5 by 6 to the power k is the probability of getting no 2 at all. So, the answer to the question is simply 1 minus 5 by 6 to the power k. So, what you have done is, instead of tackling your problem directly, you have basically divided your sample space into two sections. One is you get no 2s, and the other section is basically you get at least 1 2. The sum of these two regions is basically your entire sample space, which is denoted here as probability 1. Okay. So, what is basically given to me is that 1 minus 5 by 6 to the power k is given as 2/3. So, this is the probability, desired probability of getting at least 1 2. Now, I must solve for k to get the required number of tosses, because k is the number of tosses. So, at the end of this problem, I would get the total number of tosses required such that the probability of getting a 2 becomes 2 by 3rd. So, that would mean you solve this equation for k, and that would for example, if you take k equals to 1, this is the, if you just toss it once, then you can see it is 1 minus 5 by 6 equals to 1 by 6, and this is definitely less than 2 by 3. Okay. So, I do not get the equality for one toss. Now, if you take 2 tosses, you get 1 minus 5 by 6 to the power 2, which is basically 11 by 36. This is also less than 2 by 3. So, this way you keep on sort of increasing k. Eventually, you will see that for k equals to for k greater than 6 and above, for k greater than 6 actually, you will see that 1 minus 5 by 6 to the power k is basically greater than 2 by 3, because as k increases, 5 by 6 to the power k will become smaller and smaller, because 5 by 6 is already less than 1. So, a larger power would only make 5 by 6 to the power k smaller, which means 1 minus 5 by 6 to the power k will become larger. So, typically for k equals to 7, you will see that the probability becomes greater than 2/3. What this means is that I must toss. So, the conclusion, the take home conclusion is that one must toss the die at least 7 times. To get the probability of getting at least 1 2 greater than 2 by third. That is the conclusion. Okay. Fine. Next, I have another very simple problem, at the end of which we will close this this lecture. I will just give you one more problem where you can solve for probabilities objectively. So, let us take another, just as before, a fair sided die, okay, which means the face of a die can be 1 2 3 4 5 6, okay. So, that is the face of a die, which is mu, a variable, and can take one of these values, one of these symbols 1 to 6. So, suppose I ask a question, what is the probability of getting at least two 5s in 3 tosses. So, basically you are tossing it the first time, tossing it the second time, tossing it the third time. You have tossed this fair sided die of 6 faces 3 times, and what is being asked is that you should tell me the probability of at least getting 2 5s, which means I could get a 5 here and something else here, okay. So, this something else basically means that you could be getting 1 2 3 4 and 6, not a 5, okay, 5 is absent, and you could also get something here and a 5 here and something here, okay. So, this would be, in fact you want 2 5s. So, let me just correct myself here, you want to get 2 5s, that is the question, right. So, this is obviously not correct. So, let me just correct it. So, I am writing down all possible ways of getting 2 5s, okay. There is one more way of getting 2 5s, that would be keeping something here and 2 5s here, okay. So, since we have 2 different types of symbols, I am going to color them with different colors, okay. So, there are 3 ways in which you can basically get 2 5s out of 3 tosses. So, the probability of getting at least 2 5s out of 3 tosses is, see, the probability of getting an x is basically 5 by 6, okay, and the probability of getting a 5 is 1 by 6. So, if you look at this particular observation, probability of this observation is 5 by 6 cube, which is, if I break it down, the probability of this is, so let us write it below, okay. So, let us write it below here, yeah. So, the probability of getting a 5 is 1 by 6, and probability of getting another 5 is 1 by 6, and the probability of getting an x is 5 by 6, okay. So, which is basically 5 by 6 cube. Now, there are 3 such ways in which it is possible. You have one more way here and one more way here. So, the total probability of getting 2 5s in 3 toss, okay, of 2 5s is basically 3 into 5 by 6 cube, which is 15 by 6 cube. Okay. That is the answer to the problem. We can also ask another interesting question is and that is as follows: what is the probability of getting at least 2 5s from 3 tosses of the die? Okay. So, what we solved previously was the probability of exactly 2 5s. What I am asking now is the probability of at least 2 5s. Probability of getting at least 2 5s is equal to probability of getting 2 5s plus the probability of getting 3 5s. Okay. That is the only two possibilities, and this would be already calculated. This is nothing but 15 by 6 cube as just calculated from the previous task, and the probability of getting 3 5s is just 1 by 6 cube, because there is only one way in which you can get 3 5s. So, you can get a 5 and a 5 and a 5, and that is it. Just one combination of 3 5s out of the 6 to the power 3 ways. So, the answer here is nothing but 16 by 6 to the power 3. Okay. So, this is one way to solve it. Okay. And that is the end of this particular lecture. In the next class, we will talk about random variables in general. So, this particular lecture was about discrete probabilities and discrete random variables. We will start the next lecture and discuss continuous random variables, and this is the type of random variable that you will use throughout the course in statistical mechanics, and these random variables have a profound importance in all areas of equilibrium statistical mechanics. For example, the velocity of gas particle in this room at some temperature is a random variable, which a continuous random variable, and so any theory that we develop in the context of continuous random variables, their means, their higher moments, their cumulants would be of great importance in the theory of statistical mechanics that will develop in chapter 2. So, we will meet again in the next lecture and start off from there.